All right, everybody. Welcome back to System Software. So questions from last time. Last time we started control flow, which is really going to be project 3, the upcoming project 3. Project 2 is due this Tuesday, is that right?
Yeah.
Due 10/29?
Yeah.
Any questions on that? Any questions on project 2? Got a few questions in office hours. Everybody, yeah.
Redeclaring the same variables, int x, int x. Is that
Yeah.
a possibility? Is that something we need to warn against?
Redeclaring it, yeah, that should be a type error.
Okay.
So there's an example. There's an example in the repository for this. Let's see. There should be an example in here for that. I think it's example 0. Yeah, example 0. So this is a case where you try to redeclare it. So just like in C, can't multiply define a symbol.
Do we have a predetermined error message?
Yeah, this is in ground truth error.
Perfect.
So it'll look like that.
Okay, great.
Yeah. Other questions on project 2? Everybody set on project 2, or maybe waiting till the end of the semester to turn it in, perhaps? The few of you who are here. Okay, so let's continue on with control flow. So last time I had a version of the language without an inequality comparison, and I realized that it would be pretty hard to implement inequalities without it. So it is actually possible. I was talking with a student after class. It is actually possible if you just have equals and addition and subtraction, you can actually construct a function that will compare whether something is greater than 0 or less than 0. So you can kind of think about how that would. Anybody want to take a guess at how that might work? If you have arithmetic and you only have comparison to say 0 or comparison between numbers, how can you implement inequalities for integers? Anyone want to take a guess? Yeah. So, well, how do you check the sign? We don't have, so all you have is equality and addition and subtraction, multiplication perhaps. Yeah.
Do a subtraction and take the number and divide it by itself squared, and then check if it's equal to -1 or +1.
So, you could square the number and see whether it's equal to the original number.
Yeah.
That would work. Yeah, that would actually work. That would work. Yeah. Any other guesses or attempts? So another way you could do this is to repeatedly subtract 1 from the number and see if you hit 0. It's kind of a wasteful way, but you can do that as well. But anyway, I decided to make the language a little bit easier to have a little bit more to the language. So it's kind of a trade-off between how much you have to implement in your compiler and how expressive the language is going to be. So I changed the grammar a little bit. I added a little bit more to the grammar and a few new tokens to the grammar. So let me just go over that now. Project 3 doesn't technically start till next week, but I want to get ahead on this. Okay, so just like in project 2, we've got any number of declarations followed by any number of statements. That's the same. Declarations are the same. Just like last time, the new statements are if then else, while, and this compound statement. When you have any number of 0 or more statements between curly braces, it's called a compound statement. And the expressions is what's a little different now. So these are the new, these are all of the new expressions that you can create for doing comparisons. So I actually have this more nicely highlighted in my slides. Oops. So these are the new expressions that we can have. Now they're in the grammar here, in the syntax, they're at the same level as all the other operators. But according to the semantics of this language, they have precedence, and it's the same, just the same as plus and minus having lower precedence than times divide. Mod, these also have their own precedence relationships in relation to the other operators. So now what we have is an equality test a test for not equals, which, of course you can implement that easily with using negation. But then I've also added a less than and a greater than. So strictly speaking, all you need is equals 0 and a sign, and know what the sign of the value is. And with those two flags, you can implement all of these. But so our simple C will be a little bit more expressive. I added equals, not equals, less than, greater than, and we still have our 3 Boolean operations. So just keep in mind that these 3, not equals, less than, and greater than, there are new tokens for these. So I updated the lexical specification, and they're what you'd expect. Well, there's the C, what you'd expect in C, the exclamation point equals, like so, and the less than sign on the keyboard and the greater than sign on the keyboard, the ASCII symbols for those. So you'll have to recognize those new tokens for this language. Okay, questions on this? Questions on this so far? And we'll go into more detail about this language, what it means, and how we actually implement this in LLVM. Does anybody have questions about this this new grammar for Project 3? Yeah.
So when you say you added less than or greater than,
Yeah.
to the, I guess, grammar, does that mean that we'll see, we'll be able to, or we want to have less than or greater than terminals?
Yeah. So LT will be a terminal for the less than symbol. And so if you look at the update to the lexical specification, which is here, I've added these new specifications for those new tokens. So before you didn't need these 3 either for previous projects, and now you'll need them. So I just sort of left it to you to kind of augment your lexer as we go along. I haven't been too strict about how you have to design your lexer. Other questions? Questions on this? I've also updated the description of the semantics. So I fixed the missing modulo in this list, but here's the precedence from highest to lowest of all the operators. So negation, just like in C, I'm pretty sure, has the highest out of these. And then, of course, multiplication, division, mod, plus, minus. Less than and greater than are higher precedence than all the other inequality and Boolean operations. Just like we talked about before, equality and inequality is higher than the other Boolean operations, which is I think, a kind of confusing feature of C, but I wanted to keep it similar to C. And so just like before, you have to build in the precedence into this grammar yourself. So just like we did with arithmetic expressions, you can rewrite the grammar and do the right recursion or left recursion elimination to make it right recursive. But as we talked about last time, there's kind of a quick hack you can do to have a recursive descent parser with precedence that allows for this right recursion in a while loop. So you can look at the last lecture, and I think I talked about this a couple times. You can review those lectures to see the kind of quick way to implement a recursive descent parser that has this right recursion. You just use a while loop to do it. I think that's pretty much it. One extra thing is, I think I also mentioned this last time, that because all of these, at least in this syntax, without thinking about precedence, the syntax mixes the operations for Boolean values and integer values. But I'm going to define this simple C language to not allow that kind of mixing. So mixing of Boolean and integer types is not allowed. So if you have a plus and one side is the result of a Boolean operation and one is the result of an integer operation, I won't give you those examples, because if you try to naively convert those into LLVM, you'll actually get a type error in LLVM. And we'll see why that's the case today when we go over how this can be implemented in LLVM. So that's a design choice. That's not written in stone. It's not a natural law. That's just a design choice. And to allow this kind of mixing actually is a little bit harder for you. I'll leave that as a bonus exercise if you want to allow for these two different types, two different kinds of types, two different types in the language, int and bool. You can even add a new Boolean data type. So instead of int x, you could have bool x and int x, and allow all sorts of conversions between bool and integer and you can implement that yourself. So I'll leave that as a bonus exercise. But for the kind of normal project 3, I won't give you any test cases where we mix booleans and integers, so that way you won't have to do type checking. Does anybody remember what this notation means? Does anybody remember this? Can anyone tell me? Yeah. Yeah, exactly. So if you think of plus as a function, it takes 2 parameters. Both of them are int, so it's a tuple of ints, and it returns an int. So that'll become important later when we talk about why this mixing of booleans and integers is a problem. Okay, so let's continue on. So I kind of went over this already, but we have double equals for equality, just like in C. Exclamation point equality for not equals, less than sign, greater than sign. 2 ampersands for conjunction, 2 pipes for disjunction, and exclamation point for negation. This is just like you're used to in C. We already went over this. This is our new grammar, the additions to the grammar for project 3. Okay, so the way we're going to actually implement this in LLVM, implement these Boolean expressions, is just the same way that addition got compiled down to the add instruction in LLVM. When doing these inequalities or equalities comparisons, there's a special instruction in LLVM called integer compare, ICMP. And it works very similarly to add or subtract with a couple differences. So just like any LLVM operation instruction, you've got the operator name, some extra information like NSW for add, which I'll talk about in a second, and then the type of the operands. Yeah. Oh yeah, sorry. Yeah, y should be T1. Yeah, good catch. Y should be T1. Oh, but that messes up my boxes. Okay, thank you. So I can just go through this. So this SLT means less than for signed integers. And so LLVM has several different operands you can put here for the different kinds of comparisons you want. So for instance, equals, not equals, less than or equal to, greater than or equal to. So if you wanted to extend simple C even further to have greater than or equal to or other Boolean operations, you could use this operand. So for us, or at least the normal case of simple C, all variable values are 32-bit signed integers, which is indicated by this I32. And just like with add, iCompare takes 2 operands. In this case, we have, thank you, the register T1 and the constant 10. And it just executes this comparison. But it's different from a typical arithmetic operation in that it returns a 1-bit integer. So what is a 1-bit integer? A 1-bit integer is basically just true or false. It represents true or false. So 1 represents true, 0 represents false in LLVM. So this makes it kind of subtly different from just a regular arithmetic operation. And this is actually why we can't mix, without doing extra work, we can't just mix I32 and 1-bit integer types. We can't easily mix those. LLVM will actually do type checking and complain to you if you do that. So questions on this? Questions on the integer comparison operator, or instruction rather? Questions? Yeah.
So the T2 would be a 1-bit integer.
Yeah, exactly. So the value that T2 holds is a 1-bit integer. Exactly right. Exactly right. The return type of this iCompare is I1 or 1-bit integer. Other questions? Questions? Okay, so the way we're going to represent Booleans is the same way that LLVM does, using these 1-bit integers. And this is actually denoted I1 in LLVM as opposed to I32. So the I means integer, unsigned integer, and 32 means 32 bits. For the Boolean operations of and or, they work very much like arithmetic operations. We've got and is the name of our instruction, the type of the operands. But in this case, the type of the operands are 1-bit integers. In fact, strictly speaking, and is like can work for any number of bits, whatever your hardware supports. So and in like Intel can work for 64-bit numbers. And if you remember from architecture, it just ands each bit pairwise, each bit of the two operands that you have. But for us, we don't need to use and in that way. We only need to use it for 1-bit integers. So LLVM does support and for more than 1-bit integers, but the way we're going to use it to implement our Boolean operators is just use it for 1-bit integers. So I think this is fairly self-explanatory. Just like when you see a plus when you're parsing, when you see a plus operation, you generate an add instruction. Now when you see the double ampersand, the Boolean and, you're going to generate this and instruction. Questions on this? That should be mostly straightforward, I think, as long as you've done project 2. One little wrinkle is that LLVM doesn't actually have a unary negation operation. It doesn't have a direct corollary to simple C's negation. And I think there's probably a couple different ways to do this. There are definitely different ways to do this, but I'm suggesting you can use XOR instead. So who knows XOR? You guys should all know XOR, I think, right? So if I XOR 1 bit with some value that's 1 bit, 0, 1 with 1, what do I get as the result?
0.
I get 0. Always 0? If I XOR some bit, whatever it is, 0 or 1, if I XOR it with 1, what do I get? The opposite. I get the opposite, right? Exclusive OR. Exclusive OR means one is turned on but not the other. So if they're both turned on, it's 0. If one is turned on, which means I force one operand to be 1. So if the left operand is 0 and the right operand is 1, I get 1, which is the inverse of 0. If the left operand is 1 and the right operand is 1, I get 0. So it's a little trick to implement a logical negation using XOR. But there are actually plenty of ways to do this. And if you think of other ones and you want to implement your own way, you can even do it with branching. Okay, so that's what I'm suggesting you use for all of these 3 Boolean operations. Okay, so now we have all of the instructions in LLVM to do the Boolean operations and to do the comparisons. So let's do a little demo of what this, or let's even actually walk through it together, what this whole expression will look like in LLVM. So let me switch over to the tablet here. Whoops. Okay. What was it? Y less than 10? Is that right? Y less than 10. Okay. Okay. So the first thing to look at, so I'll go through like code generation algorithms next time, but let's just kind of informally do this intuitively. And I think your homework for today, one thing I want to mention is I forgot to put up homework on Tuesday, but I put it up, I don't know, Tuesday night or Wednesday. So there is a homework from last Tuesday. If that really screws up your schedule and you can't turn it in on time, just let me know next Tuesday. But there is a homework from last Tuesday. It's homework 15, I think, on web courses. And there's another homework for tonight as well, which is exactly what we're doing right now, just taking expressions and turning them into, taking code and turning them into LLVM instructions. So sorry to drop that on you. You all look very surprised right now. But if it's a problem, let me know. I realize that it should have come out Tuesday. Yeah.
It says homework 15 and homework 16 Tuesday next week.
Okay, I will fix that. They're supposed to be due a week after.
I've got one due the 29th and one due the 31st, which seems right to me.
Oh, okay.
I don't know, you check it.
I'll check it. I'll double check it. So apparently one, yeah. I'll double check it. I'll double check it tonight.
Yeah, I
I have 29, 31st.
Okay, so it's okay.
As far as I know, again, probably don't.
Does it look okay? Okay. So yeah, let me know if the deadline is an issue because you lost a day to do it. So just let me know. Okay. So and the exercise is related to this, where you're for today's homework, it's gonna be taking a program that has if for while and writing out the LLVM equivalent of it. And so we may not get to all the code generation today, but it's due in a week, so you'll have time to go over it, and the TA can go over it in lab next week as well. All right. So the first thing, for the first thing we need to do in evaluating any operation in Simple C or any of these languages that have order of operations is to figure out the order of operations, which operations get executed first in this example. So which of this gets executed first? What's that? X times 3? Yeah, good. X times 3 is executed first. And then what's executed after that?
The x times 3 not equal to 0.
Right, good, yeah. These parentheses. What's after that? Y minus 10, good. Y minus 10 is next. Then what operation is next evaluated?
The end.
The and. Okay, good. I'm not trying to trick anybody. You can call it out. Okay, so let's write roughly what the equivalent LLVM IR will look like when we do this. So let's just assume that X is allocated to T1 and Y is allocated to T2. So what's the first operation we do in LLVM? Well, let's let's do the loads. That's a good idea. Let's do the loads. We'll assume that I didn't make that clear. So let's load T1. So we're loading, and I'm just going to do kind of LLVM pseudocode. And then what's the next thing? What's the next operation that happens? It's the multiplication. Yeah, it's the multiplication is the first thing that happens. So T4, and then we do this multiplication. I think there's a no sign extend here. What's my first operator? T3, because that's the value of X. And what's the second operator? 3, because it's just the constant. Okay, and the next operation I do is this inequality here, this not equals to expression. So does everybody remember what that is? Yeah, it's an ICMP. ICMP is the instruction. And yeah, go ahead.
Is there a difference that you have to write to if it's equal or not equal?
Yes, yeah. So I was just about to get to this. So the operand that goes here is the type of comparison that you want to do. So in the case of not equals, it's any in LLVM. So I think
Okay, you wrote EQ in the example thing.
Which example?
Inside of the project 3 instructions, you wrote EQ in that.
Okay. I'll fix that, or do a pull request if you'd like to fix it, and I can merge it. But I'll check it out. Okay, so there are, let's see, did I? Oh yeah, so this is documented in Project 3 and also in the LLVM documentation. I was wondering if I put it in the slides, but it's in the Project 3 README on the website, and it shows you the different operands you need for equals, not equals, greater than, and less than. So it's any for not equals, and as someone said, we need to create a new temporary variable to hold the value of this comparison. And we're comparing 32-bit numbers. And so what are the two things that we are comparing? T4, good. T4 and 0, good. So that's our second operation that we have to do. Okay, so what about the third operation? Y is less than 10. So make a new temporary variable. It's I compare. And for less than, we use signed less than. because we have signed integers.
I'll load it first.
Oh, you're right. Thank you. Oh, thanks. We have to load it first. So yeah, we got to load y.
Yeah.
Thank you. And now we can do the comparison. So we do a signed less than comparison of two 32-bit numbers. And we're comparing y with 10. All right, and then the final last thing that we need to do, what's the last operation? The Boolean AND. So let's make a new temporary variable. Let's do the AND. And what is the data type of the operands that we are comparing? I1. Yeah, good. They're Booleans. It's I1. Yeah, good. And so it's, yeah, so T5. These are the two comparisons that we did. So T5 holds the first comparison, the left operand. T7 holds the second one. Questions on this? Yeah. Oh, I'm sorry. This is I1. This is my bad handwriting. Yeah. Oh, yeah. So greater than would instead be like SGT is greater than. So I compare. It can take more than these, but it can take. For us, we just need equals, not equals, signed less than, and signed greater than. Yeah, you can do those as well with LLVM. It supports them, but Simple C doesn't have those. So Simple C only has those four. Only has those four. All right, questions? What are your questions on this? Yeah.
This might be dumb, but how would we determine whether to print out an I1 or an I32? Is it just because an AND is always Boolean, or? That's
a really good question. Yeah, how do we know whether we need an I32 or an I1 for our operations? So what do you guys think? Yeah. Well, that's what I said. So what does that mean? What does that tell us? If we're not mixing Booleans and integers. Okay, yeah, good. So and or will just always be I1. Because I said we're not mixing any integers or Booleans, you can just assume that the arithmetic operations are going to be 32-bit and the Boolean operations are going to be 1-bit. Yeah. Yeah. Yeah, that's right. Equals is also. Oh no, I'm sorry. Okay, so equals is returns a Boolean. So for instance, say again. Yeah, so that's equivalent to this not equals here. So for the not equals, the parameters to equality are always 32-bit numbers, whereas the return value of the equality is always a Boolean. So if you forget this or want to be reminded of it, this type specification here tells you in that nice type specification what the inputs and outputs of all of these operations are. This is actually what's so useful about formal type theory, is that it gives you a formal mechanical way to describe and actually check the types of your program. So I've made it a little easier by not mandating type checking, just saying that nobody's going to give you a bad program. But if you remember our talk on types actually are an automated way to prevent these kinds of programs from even getting to the machine. And I'll actually go over doing this type checking for Booleans and integers today. Yeah.
I'm guessing it's not included the greater than and equal and less than and equal.
So I was a little lazy here, and I put them here. I said that equals is the same as these. So plus for all the arithmetic operations, it takes two integers, returns one integer. For unary negation, it takes a bool, returns a bool. For all of the comparisons, equals, not equals, greater than, less than, it takes two integers, returns a Boolean. And the Boolean operations take two Booleans, return a Boolean. So that question, that was actually a really good question about how do you know whether to use I1 or I32, because technically and can take I32. You can do a logical and of two 32-bit numbers. And why is it that for our language we can just always assume it's I1 and I32? So that's a design choice. That's exactly why I made this design choice to say these operators will never be mixed. To make that a little more formal, what that means is that these are the types of our operators in our language. Because this double ampersand can only take Boolean values, then it can't take 32-bit integers. That's what this type specification says. But then it's up to us as the language designer to actually enforce that if we want to, or tell the programmer they have to enforce it. Yeah.
So this means that actually type programs that we test on will never have like two numbers.
Right. Yeah, I won't give you programs that violate this type. I'll leave it as a bonus exercise for those who want bonus points to deal with programs that that violate this type specification. So that's implementing type checking. And I'll go over examples of that algorithm today. It's the exact same type checking algorithm I showed you a couple weeks ago, but this time we actually have more than one type, so it's a little bit more interesting, like relatively more interesting. Okay, questions on this? Questions on that? So that's a really good question. Why is it that you can assume these are I1 and I32? Questions? Any other? Yeah. How do you perform logical and? You just, I guess it's bitwise and. Yeah, maybe. Yeah, sorry. I think it's bitwise and. Yeah. I can actually double check. Let me see what they call it here. So this is the LLVM reference. What do they call it here? Oops. Oh, they call it the bitwise logical and. Okay. So it is the logical and. I think it's only logical and. The bitwise logical and. So you can see here it allows any type. That's what this means. But it'll, you can see here's an example of using it on a 32-bit number and what it yields. Yeah, so for the bits for 4 and the bits for 8, they don't share any ones in the same position, so the result's 0. And these will ultimately correspond to like Intel's. If you're compiling for Intel, it'll compile down eventually to some Intel instruction. So, wow, this is 256-bit. This is some processor extension. Okay, anyway. Where am I? All right. Oh, really good questions. Really good questions. So then we went through that, went through the demo. Okay, and this was exactly what I wanted to get to anyway. So how can we actually guarantee that the Booleans are I1 types? In C, this is a little bit more strict than C. In C, I can happily write an if statement that just takes 207 as its condition. I can, to show a quick example, C has no problem with me writing a program. Let's see, let's make this input value. C has no problem with me saying something like this, where my condition is, in this case, a 32-bit signed integer. And to kind of prove that, I can quickly write a program just so it doesn't give me a warning. And so it'll happily accept pretty much anything in your condition. It'll always be able to use it as something. It'll basically say if the value of that is non-zero, then it's true. If the value of it is 0, then it's false. So let me just compile this real quick. Oh, so it's always non-zero, basically.
Yeah, it's the name of the program.
Yeah, the name of the program. So I can force it to be 0, for instance.
There you go.
And you can see that it doesn't get printed out. Or I can say argc minus 1. And that'll do what I really wanted. So if there's one argument, it'll print it out. So, but anyway, and you can even put pointers here too. So I can use argv, which is a pointer, and it'll happily compile this with no problem. If you were to look at the code, it would do some, it would actually generate code corresponding to what you'd expect. It would like compare it to 0 or non-zero. Let's actually look at the code. Do you guys want to see the code for this? The assembly? Let's turn off optimization. Oops. Oh, because I have the output. So let's see what it did. Does this, here's the compare. So it's comparing directly with an offset in memory. And if we look at the specification for Intel's compare Q instruction, it compares 64-bit register. Yeah, so it's a 64-bit compare. And Intel's a little different because they have this flag register. Did you guys learn about flag registers? So instead of like an LLVM where we explicitly return a bit that represents the result of the comparison, notice here in this assembly code, there's no left-hand side to any of these operations. The operations are just instruction, here's your 2 or maybe 3 operands. So where does that go? Well, there's this flags register in the Intel architecture that holds it gets set after every instruction. There's some bits that are set after every instruction, and one of those bits is was the resulting value equal to 0, for instance, or were they equal or not? Let's see where that is. I guess this is the parity flag. No, that's not it. A 0 flag. Yeah, it's one of these things. Yeah, 0 flag. I guess that's it. I'm not exactly sure which one it is, but you can even look. You can like read over the specification, and it'll tell you exactly what the. Whoa. So if you actually look at the specification of it, so it'll say, set the flags registers and so on. So anyway, LLVM abstracts all that machine dependency away. And C kind of is very permissive. Its type system is very permissive. It'll do a lot of hidden type conversion for you, or just sort of ignore types and not really care about types, like in the case of conditionals, where it'll just sort of leak the underlying representation to you. But in more high-level languages, these kinds of type mixing are not allowed. Like in Java, for instance, well, Java actually I think simulates C's behavior. But if you have a Boolean type and you try to use some other type with it, the Java compiler might complain to you. I think it kind of also adopts some of the C type coercion. But there are languages like Ada that will actually complain if you don't have the exact same type in your operators. Okay, questions on this? Questions on this so far? Okay, so as I showed on the project through description page, these are the type specifications for all of our operators. So just to go over them once again, the arithmetic operations take 2 integers, return an integer. The comparison operations take 2 integers and return a Boolean. So these comparison operations is how we move from integer types to Boolean types. That's why we can have an expression. The whole expression may have integers and Booleans in it, and Boolean comparisons. But it's completely type safe because comparisons take integers and return Booleans. And that's what a comparison does. It takes 2 numbers and tells you some property of them, some true-false Boolean property of them. And then we can combine the results of those comparison operators with our Boolean operators. Okay, so if you want to undertake this bonus project, or just sort of understand how this kind of type enforcement can happen, we can use type checking, same kind of type checking we talked about a couple weeks ago. And the goal of this is to guarantee that I1 is used only in Boolean operations, at least for this definition of the language that I'm giving you. You could certainly change the language to have C-likes type coercion, but if we want to enforce that it's always I1 for an AND instruction, this is what we want our type checker to do. And so if the type checker finds that it can't prove that every Boolean operator is using an I1 type or a Boolean type, then there's a couple of things that the type checker can do. So in some languages that have stronger type systems like Java and Haskell even, although there are ways around the differences between numbers, or Ada, you can just reject the program, not the programmer. That's a little too harsh. Reject the program. All programmers never be rejected by the compiler. The compiler will happily recompile your program. So reject the program, and it requires you to rewrite it to get around the type. And I'm sure you've all struggled with the type system of C, especially of Java. I'm just saying, why doesn't this compile and struggling with it? But you can also use this information, use the knowledge that you have from the type checker to say, well, I can do this conversion automatically for the user. And there are actually instructions in LLVM that are specifically designed to change the type of variables. So for instance, if you have an I32, you can truncate it to be an I16 type. And there are explicit instructions in LLVM to do this that correspond to low-level Intel instructions or ARM instructions. So as I said before, I'm not going to give you any incorrectly typed test cases. I'll leave the type checking as a bonus exercise. So there are two possible bonuses you could do here. You could just add type checking to make sure that the expressions are well typed. And you can even go a step further and add an explicit Boolean type to simple C. So you can have variables that can hold Boolean values rather than having to hold 1 or 0 and then comparing with 1 and 0 to see if they're true or false. Okay, so let's look at how we can do this kind of type checking on these expressions. So let's get back to let me just copy down one of these examples. Oops. So it was x times 3 not equal to, what did I say? I can't even remember. 0, okay. It's late. And y less than 10. Okay, so let's quickly make the parse tree for this. The multiplication is the lowest level operand here. The not equals is the next lowest. Then we've got the less than. And finally, we've got the Boolean and. So you notice every time I seem to have a different parse tree structure. I'm kind of being a little fast and loose with this. So this is really just like the classic expression tree structure. Another way to write it is to put the operands here as the node itself. Any questions on that? Any questions on the way I'm doing the parse tree or syntax tree? If you have any questions, please feel free to ask me, because I'm playing a little fast and loose with this and not being super formal with the expression tree. So we're not going to talk about it so much in this class, but you can think of this as an abstract syntax tree, a parse tree that removes information that's unnecessary for compilation. This is what real-world compilers do after they parse. Rather than generating code, they'll typically produce this tree structure that throws away information that's not necessary for compilation, and then they'll do all their operations on that tree. Okay, so who remembers the type checking algorithm? Does anybody remember the type checking algorithm? What is it?
Well, you have the 2 inputs and then an output.
So that's for one. Okay, yeah. So if we know the types of the left and right operands, and we know the type of the operand, we can type check it. So if we know that multiplication here has, so what does multiplication have? What's the type of multiplication? 2 ints. And goes to int. So that's our type specification for multiplication. And we know that x, so how do we know the type of x?
We know it's an int for
Symbol table. Good. Yeah, the symbol table holds the type information about the symbols. So the symbol table tells us that X is an int. What about 3? How do we know the type of 3?
It's just a number.
3 is just a number, so depending on how we define our language, 3 is going to be an int. For us in simple C, we only have the int data type, at least for explicitly declared types. So we just, as kind of an axiom, say 3 is an int. This symbol 3 is an int. Because, remember, keep in mind, this is an ASCII number 3. It has no meaning as a number to the machine until we, as the compiler writers, translate it to a number. Of course, the way we translate it was just write it out as ASCII for LLVM. But if you were generating machine code, you'd have to, well, depending on how you do it, you might have to change representations for int. Okay, so the basic type checking algorithm is when we are at this parent node, the node representing the multiplication, we take the specification of the operator and we check it against the left and right children. And we see that, oh, okay, these types match. And then what? What do we do once we know that these types match? We know that the operator's types match. Say again? Yeah, so that tells us that the result of the operation itself is an int. Oh, it almost seems like trivial, right? I mean, to you, I mean, we're all human, so we're all very good at looking at this and sort of intuitively doing this. But remember, we're writing a program that's doing this automatically, a program that can, without you having to think about it, prove that a program is type safe. And so what we've done is we've actually created what is the recursive step of this type checking algorithm. The recursive step says when we're on a node, in order to, if it's an operation, in order to check the type of it, we look at its left child, we look at its right child, we see if the arguments to the operation match, and if they do, we say that this node itself has type int. So a more kind of mathy way of looking at it is that each of these leaves is like an axiom in our logical system. So the axioms are just the definitions, the base rules of your logical system. And that this type checking step is like a step in a proof to prove that the entire expression is well typed. So each time we apply one of these rules, and recursively, we can prove that the entire expression is well typed. And so that's our recursive step. So if we were to apply this from the entire tree, we'd start at the root node and say, well, what is the type of the root node? That's what we're trying to prove. Our theorem is that it's well typed, or that's our theorem. That's what we're trying to prove. So when we apply our recursive step, what do we do to apply our recursive step? Yeah, we look at the left child and we look at the right child. And because this is a post-order traversal, we get to the left child first and we say, okay, what's the type of that? How do we find the type of that? We look at the left child and we look at the right child. So when we go to look at the left child, we see that we've got this multiplication operation and we're now at leaves. So those leaves are just axioms in our proof that say, well, okay, I don't have to prove that X is an int. I just, the programmer told me it was an int. So I'm just going to assume it's actually an int. And the definition of my language for 3 tells me that 3 is also an int. So now, just like when you do math proofs, you can just assume, okay, here's the definition of these axioms. X is int, 3 is int. Yeah.
So, because like these are expressions and you already have like a recursive expression.
Yeah.
Function, I guess.
Yeah.
We kind of like work things so like storage of these types are expressions.
Work the storage of the types? You mean the actual values?
Yeah, like yes. I'm trying to just like merge like the algorithm the expression function.
Yeah, you could do this type checking while you are generating code. You could certainly do that. Yeah, you could merge it. So if you wanted to take that bonus project and actually do this type checking, the way you would do it is in addition to returning the temporary variable, these algorithms are like, it's like all the same algorithm. If you want to evaluate the expression, you return the actual value. If you want to compile it, you return the register that holds that value or the memory address that holds that value. If you want to type check it, you return the type. And you just apply different rules at each recursive step. So you can kind of abstract this away into like the same post-order traversal function, but the behavior, the processing you do at each step depends on what you're trying to accomplish. So yeah, you could certainly integrate this with your code generation. And so if you wanted to integrate this with code generation, instead of int, this would be I32, right? For LLVM, int means I32 in LLVM. We can just translate those types. Yeah, so you can totally integrate this with the code generation step, because the parser is really just a tree walking algorithm. It's really just walking this parse tree. Okay, so we've now gotten to the bottom of the tree. We've gotten to the axioms of our little logical system here that tells us the types of x, the types of 3, and also the type of the operator itself. And then we apply this proof rule, you could say, to prove that the type of this star node, the type of this multiplication node itself is int. So we've proven that. We have two axioms, x is an int, 3 is an int. And by this proof rule, int the multiplication takes two integers and returns an int. That rule, we can conclude that this parent node is also an int. All right, so we're deep in this recursion on this tree. So we have now proven that the left child of this node is an int. So then we need to look at the right child of this node. And so it's 0. So of course 0 is just defined by us to be an int. And now we've got this not equals expression here. What is the data type of not equals? Boolean. So this is Boolean. So let's apply our proof rule. Our proof rule says we have to match the arguments. So we have two arguments int, and we're trying to see if that matches the arguments of bool. But bool is just a primitive data type. Bool is not the type of an operation. So the not equals operation itself couldn't just be bool. We know that it returns bool, and so in our type specification format, we know that arrow bool, that means that it returns bool. So yeah, not equals returns bool, but what is its full type specification for the not equals operation itself? Yeah, it takes two ints and returns a bool. So I think in the parlance of like the formal type people, they'll call a type like int, they'll call that a primitive type because it only represents a range of values. Whereas, actually, I don't even know what the term for this is, aggregate type maybe, or compound type. So this whole expression here itself is a type, is one type of something. It's a type of this symbol in our language. So it's not that there are three types here. I mean, there are types that it operates on. But you can think of the operator, this entire function's definition, function declaration, as being itself a type, a function type. And a function type is this aggregate type or compound type. I can't remember the term, but it's a type that includes the arguments and the return type. Yeah. Yeah, so it would correspond to, well, that's actually an interesting question. So what does this mean to take two integers and return a Boolean in LLVM? So in LLVM, that would be the types I32 goes to I32, or I32 goes to an I1. But the operation is not this not equal sign. The operation is this I compare, not equals. And if we were to look at the specification, if we were to think about the type specification for I compare, its type specification would be exactly this. takes two I32 bit, or two 32-bit numbers that corresponds to these arguments here, and it returns a 1-bit argument. So the LLVM language reference may not actually use this notation, but in their description of the language, they say this. They say it will return a 1-bit integer. So if you try to use that 1-bit integer where a 32-bit integer is needed, you'll get a type error from LLVM. So you can think of this kind of shorthand notation. It's kind of a formal notation for specifying types. It's popular in the formal programming languages world, but it's in every programming language that has types. Even if it's not expressed this way, the idea is expressed that functions can only take certain types and they can only return certain types. So if you remember way back when we talked about typing, the purpose of this is to constrain values to be constrain variable symbols to be a certain range of values and constrain which operations can be executed on them. And by kind of expressing it in this formal way, you can use very fancy math notation to express this pretty simple idea that you have to type check in order to allow the program to be safe at runtime. And if you take programming languages with Dr. Levins, I think some of you are, and you go to Haskell, they use notation that actually kind of looks like this in the programming language for defining types.
You just need a second colon.
What's that?
I think you just need I think in your slide was plus colon. I think it's just 2 colons.
Yeah, maybe it's 2 colons in Haskell, but the colon just says this is the data type. The symbol is first, the data type is second, separated by colons. In C and Java, the data type is first. Okay, questions on this? I think I got off track only a little bit. All right. So the type of this not equal symbol, it takes 2 integers and returns a bool. And we'll see why that's kind of important here. In order to type check this, we have to check, are the 2 arguments integers? And we see that, yes, the left and right-hand side, they're both integers. But this type specification tells us that the return type is not an integer, not like for arithmetic. The return type is a bool. So this is how, in this type checking process, even though we're mixing booleans and integers in the same expression, they're never going wrong. They're never mixing integers and booleans in the same operation. And the reason this is possible is because there are some operations here, like not equals, that are explicitly designed to take 2 integers and return a Boolean value. Questions on this? Okay, so let's finish off this type checking. So now we found that the left-hand child of our top node is Boolean. So we now need to figure out what the right child is. So how do we know what the right child is for this node?
By resolving what y less than 10 is.
Okay, good. So we have to resolve what y less than 10 is. So how do we do that? Look at the children. Yeah, look at the left child. So we see y here. And how do we know what the type of y is? To beat a dead horse, good. We look at the symbol table, tells us that it's an integer. How do we know what 10 is? Because we defined it in our language as an axiom that this symbol, that is a set of digits, ASCII digits, we define that to be an integer in our language. We define that. You can make your own language where 9 is represented as the integer 1 in the machine if you want. You're free to do that. But we've defined the symbols 1, 0 to be an integer. Okay, and what about less than? We have this less than. What is the data type of less than?
It takes 2 instances.
Good. It retakes 2 integers and returns a bool, just like not equals. And now we find that the left and right children match the arguments of this type. So that tells us we can infer that the resulting type of this operation is a bool. So in logic, this is basically like inference. This is like if then else in logic. So if you have the 2 arguments as integers, you can conclude that the result is a bool. All right, so finally, we've got this ampersand, or these 2 ampersands. This means Boolean and in our language. What is the data type of Boolean and? Say again?
2 Booleans, 2 Booleans.
Yep. Each argument is a Boolean, and it returns a Boolean. So when we go to check, the left side is a Boolean, the right side is a Boolean. So we can conclude that the entire expression results in a Boolean. And QED, proof done. Right? So math is like programming. You can actually program math now, right? You don't have to do proof by hand as much anymore. Yeah.
Would it be possible in project 3, like let's say with the y less than 10, should we just replace that with 1 or 0 and that would still be perfectly acceptable?
Wait. So, I'm sorry. Say again.
So let's say in that line,
Here?
instead of y less than 10, just replace the whole thing with 1 or 0. Would that still be perfectly appropriate?
Oh, that's a good question. Yeah. So what happens when we have what's an example where it won't type check? So I'll do that next as an example. So, but are there any questions? Any other questions on this? Questions on this? So the kind of amazing part about this is that type systems and type checking is pretty much equivalent to math proof. And there are programming languages with specially designed type systems that allow you to express the full range of logical proofs. And you can actually write programs in order to write proofs. And these proofs will be machine checked. So if you kind of hate writing proofs in math, which is not so fun to do, but you like programming, then you can actually kind of console yourself that math is not that bad. It's actually basically just programming. That's what all those mathematicians are doing, you can say, maybe, even though that predates computer science by several thousand years. But yeah, I mean, it's kind of a cool result that this little type checking algorithm is actually doing a proof about the behavior of the program without running it for all possible inputs. Okay, questions on this? Questions on this? So feel free to write this and let me know, and we'll check it and give you bonus points for it. Okay, so it's a good question. What happens, well, let's use the same example here. What happens if, say, the left-hand side, well, let's do, can I edit this? Can I edit this one? Should I destroy this one? Okay, let's destroy this one. So let's back up and replace this right child here with what your classmate suggested and just put, say, 10. All right, what's the type of 10? It's an integer by definition. So now we are at the root of our tree. We've seen that the left side is a bool, the right side is an integer, and we've got our operator, which says the two operands must be Boolean, and then it'll return a bool. So one of the operands is not Boolean, therefore the types don't match. Type error. Yeah, so it depends on your language. Depends on what you as the language designer want to do with this. So in C, well, C doesn't even really bother with Boolean. I mean, it depends. I think it's kind of compiler dependent how they even will implement this ampersand, because you can actually implement ampersand, which is done in C with using compare and branch to do short circuiting. We'll talk about this more when we talk about if then else statements. But in language that'll do kind of strict type checking, where you actually explicitly say these are two different types, you can just return a type error and say, I'm not going to accept this program. I'm not going to translate it. That's one of your options. Another option is to define these rules about type coercion. Like, can we, is there an operation that will turn int into a bool? So we can, let's see, I don't know any symbols for this, but we can make a new operation called convert that takes in an int and returns a bool. And what we can do is when we see this case where we want to check that there are two Boolean operands, and if we see an int, we can automatically insert this convert operation. So we'll kind of interpose along here this convert operation. We'll just insert that ourselves. And this is exactly what the C compiler does. It'll insert machine code that'll convert between types, either truncating types or extending types, zero or sign extending types, depending on the type. And so when we do that, convert is defined to take an integer and return a bool. So the result of this new node here will be a bool, and voila, our program type checks. Yeah, that's it. You can just insert, you as the programmer can insert code wherever you want, do as the compiler writer. You can always just do whatever you want with the output code. Because it's up to you to define, what you want your language to be. If you don't want your language to accept this program, reject it. If you want it to accept it and force the types, you can accept it. If you want the underlying machine representation to leak through like C does, you can do that as well. Okay, good question. Any other questions on this? Other questions on this? So please feel free to implement this. I think it's kind of a cool and really pretty straightforward algorithm. If you get the code generation down, doing the type checking is really not that bad. Okay, so let's sort of preview implementing if statements, and we'll see how far we get in a few minutes. And yeah, so if statements, as you all know, the if statement means each branch is a mutually exclusive choice. Only one of these branches, if at all, is going to be executed. So if you have a whole stream of if and if then else statements or a switch statement, one and only one, or one and one or zero of these branches is going to be executed, no more. And so if we think about how we actually implement this in machine code, we can use branch instructions to do this, because branch instructions are able to jump past code and just leave certain code executed. And the choice of how we branch depends on the result of this conditional expression. So we've already seen how we can compute these conditional expressions using LLVM, or generate code that will compute it. To see where and how we insert these branch statements, let's look back at this flowchart representation. So if I have this program here, it just defines and reads in x. And our if statement checks whether x equals 10. If it does, then we should execute this print statement. Otherwise, we skip it and just execute print 0. So if x is equal to 11, what should my output be in this program? Print 0. If x is equal to 10, what should my output be? Just print 10? Print 10 and 0. Oh, catching you guys. You guys must be getting tired. Yeah, it'll print 10 and then it'll print 0. It'll always print 0 because this print 0 is outside of the if block. That's our meaning of the if block, right? So the way we can represent that in a flowchart, the kind of useful representation, is we represent the conditional as the last statement inside of our block. And then we have two branches representing whether this Boolean condition is true or false. If it's true, we print out x and then continue on to whatever's after our if statement. Otherwise, we just skip the inside of our if statement body and print out whatever's after it. So the way we can turn this into code that has branches in it, LLVM does not have if statements, machine code doesn't have if statements. The way we can turn this into code that has branches is at these points where we're checking what the condition is, that's where we insert a branch. And these points that we are jumping to continue past these branches, that's where we insert our targets for our branches. So in LLVM, the way you do branching is with the BR instruction. So the BR instruction takes a 1-bit condition. It's 1 bit, right? That's the Boolean value that we're generating. Takes a 1-bit condition, and depending on whether that bit is 1, it'll jump to this label. Otherwise, it'll jump to the second label. So it takes 3 operands, a bit value, which is 1 or 0, the condition value. The first one will be taken if the condition is 1. The second one will be taken if the condition is 2. So this makes it a little bit easier than programming in, say, like, probably even MIPS or Intel, where you can only branch to one place, right? I think in MIPS, that's also the case. You can only branch to one location. So LLVM kind of makes this convenient for compiler writers because it gives you both branches that you can branch to. The way you specify where you want to branch to is you use this label syntax. And this is the same in C and assembly, where you put the name of the label followed by a colon. And so notice here that the labels are given with a percent sign, which is the same as what we use for registers. And we say label before it, but it's the same syntax we use for registers. And that's because program locations themselves are memory addresses. They're also memory addresses. So they're also kind of like register values. Yeah. So yeah, this specifies what the location you want is, and this is how you actually branch to it using the branch instruction. Yeah.
So, just like with the temporary things, we should never reuse the name of a branch label.
Right. Yeah. Yeah. Just like any other registers, never reuse the name of it. So I'll talk next time about code generation, and you can just do this. There's many options you can do. You can just use your temporary variable generator to do this if you want. Just reuse that. It works. And so last final thing, if we before I'll leave it here, but the branch instruction, you insert it right here, right after you do the comparison, and the labels get inserted right before the print X and the print 0, however they're translated into LLVM. Okay, so let's leave it at that. Next time we'll actually go into generating complete code for if statements and branching. Yeah, here's a complete example. This is in the project 3, but let's end it here, and I will see you guys next time.
Have a good weekend.
Hey, oh yeah, everyone have a good weekend. Thank you.
So many.